All right, guys. Let's just give it another minute. We're good. How you guys doing? Just taking a look at the classroom here. It's neat to see from here. Okay, great. Oops, sorry. Okay. So let's go ahead and get started. So we, just as a reminder, some stuff that's, things that are coming up. So today, we have our quiz opening up at noon. So from 12 noon today until 12 noon tomorrow, you have the quiz availability window, in which you can start the quiz. You have 30 minutes to take it, 15 to take a picture and upload it. Remember, PDF format is preferred. I will take JPEG, but I prefer PDF. Let's see what else. The homework is due tonight. The homework for chapter 1.3 and 1.4 is due tonight, so make sure you have that in. If you are resubmitting a homework for points back, just send me an email so that I know to take a look at it. I may not otherwise notice, and you want to make sure that you get credit for having done that. Okay, so we are going to continue on today talking about chapter 1.5, okay, which is about extreme values. Okay, places where our function is doing something interesting. We want to be able to figure out how we're going to describe that function. Here. So we left off last time talking about maximum and minimum values, but we said that there were exceptions to that rule. So say, for example, I've got a function that as my x is increasing towards infinity, my function's always increasing. As my x decreases to negative infinity, my function's always decreasing. So I don't have any maximum or minimum along this function at all because it's just completely unbounded in both directions. Also, I could have a case where I have a discontinuity on my function, where along this interval a to b, I should have a maximum value, okay? But my maximum value actually doesn't exist because my function is undefined there, okay? So I'm basically going to say because of this discontinuity, I don't have a maximum value, okay? So it was just a recap from what we had covered yesterday. And today we're going to pick up and we're going to keep talking about that. So bear with me today. We've got a bunch of definitions that we need to get out there. Make sure that you guys all have, you know, in your mind's eye. And then we're going to work through examples and we'll talk about what things mean, especially through our examples. Okay, so another exception to our no maximum or minimum rule is something if we have an open interval. And how that would look is, say, for example, right, here's my x-axis, here's my y-axis. Right, here's my A to B. Like say I want to be looking at A to B, but A and B, draw them out like this. A and B, what happens here at a particular value, my function is undefined at that spot right there. And then it increases without bound as I approach my other end of my interval. Let's call this function g of x, okay? So along this open interval, how we would write this out or how we would describe it is that g of x is defined along this open interval. We write it A to B. See, our brackets are smooth so that it basically means that we're not going to include A and B. G of x has no maximum value, right? I would expect to have a maximum value. Here my function's increasing, but I have no maximum value because the function tends to infinity, it's basically, it's going to positive infinity as we head towards B, that other end of our interval. Okay, so I should have a maximum value, but my function's unbounded essentially, and it never quite reaches my my interval itself, the bounds of that interval. The function also, g of x has no minimum value, right? On this end, I would expect to have a minimum value here, but I have no minimum value because while it tends towards the minimum, right, on the left, as g of x, as x approaches a, g of x does not take on that value. Right? My function's undefined at that spot, so I have actually no minimum value there. Okay, so it never actually realizes, never actually gets that value. So this is our open circle. Function's undefined at that spot. Okay, so these are exceptions to our rule. We have a discontinuity. I've got some open interval with things happening on my function that make it so that I don't have a max or a minimum. Okay, or like we showed at the first case, that our function itself doesn't have a max or min because it's always increasing or it's always decreasing. Okay, so let's draw a picture. We're going to talk about what things look like when we can get stuff. And then we're going to talk about the process of actually how we get those values. Okay, so let's talk about, we have a closed interval. So it's going to look like this. My function has some value here. My function has some value there. And okay, so this is my function here. Let's say we'll call it f of x. And then here. Okay, so this value here, so let's say our interval, we're going from a to b. It's a closed interval, so we're going from a to b. This value right here is our maximum along this interval, a to b. Okay, maximum on, we'll call it on a to b. This right here is our minimum on our interval a to b. Okay, right, within, and we're going to talk all about this whole chapter. We're going to talk about, like, actually, how do I find these values and what's the process of actually finding these values. But along a closed interval, right, this is what it could look like, where I have actually a maximum and a minimum that's going to be defined. Okay, my function is continuous. On my interval, and that's important, right? So it's going to allow me to do a bunch of stuff because it's continuous. Okay, so let's talk about what that means. So I've got some definitions and some theorems here, so bear with me here as I put up words. We'll put the words down, we'll discuss it, and but then we'll actually get into the meat of it in a minute. So we've got the existence of extrema. Remember, extrema means local max, local min, or absolute max, absolute min along some interval. So extreme values on a closed interval. Okay, so we've got this continuous function. F of x, right? This is our f of x here, continuous function f of x on a closed interval. We'll call that a to b. Say, for example, okay, it's bounded, right? This interval is bounded. But this interval I is bounded. Okay, and then our function takes on both a minimum and maximum value in our interval. Okay, so if we have this closed interval, our function is continuous, it's highly likely, right? It's almost guaranteed that we're going to have some kind of a max or min along this interval. Okay, this whole process, optimization, is a process in which we're going to be able to find out what those values are. Okay, so let's talk about that. So how do we actually find these? Find extrema and critical points. And I'm differentiating out extrema and critical points because just because some things are critical point doesn't make it a minimum or a maximum. We're going to talk about that today, how we actually figure that out. So let's talk about our local extrema. Okay, so local extrema. So first off, we're going to talk about a local minimum, oops, I can spell, local minimum at x equals c. So x equals c is our local minimum if f of c is the smallest value, is our minimum value of our function at some, oops, on some interval. Okay, but the interval is within our domain. Okay, so our local minimum is the one in which gives us the smallest value of our function within this interval. Our local maximum, same thing, only it's going to be our biggest. At x equals c is value of x that gives the maximum value of our function in this interval. Okay, so I've got this interval a to b. Basically, I look and I say, which value within this interval gives me the greatest value? The greatest value of my function, that's my local maximum within this interval. Okay, same thing for my local minimum. So these things are going to look like, right, so my function, does something like this. I've got some kind of, like, okay, so I've got some kind of function. This is my c value. This is my local maximum. These are my local mins. Okay, this is on some open interval, right? Now let's say we bounded, we had some kind of closed interval, a to b. Okay, so here's here, here's here, here's here, here's here. Okay, so now what happens is this, right? Along this interval, right? My interval is a closed interval. This is the highest value of my function along this closed interval. So this becomes the absolute max on our interval, okay? This value here becomes our absolute minimum on our interval, right? It's the lowest value along this interval here, okay? This is our local max value, okay? So we're going to talk about how we check these values, our endpoints and our critical points, what we need to do, okay? So the first thing we do is how to find this, find extrema. Our first step is, I want to find where derivative is equal to 0. Like what x values are going to give me where the derivative is equal to 0. Okay. Then the next thing is I have to check the endpoints. Okay. So I've got a couple things that I need to check, right? Where's my derivative equal to 0 and what are my endpoint values? Okay. We're going to talk all about that as we go. So don't worry if it doesn't quite make sense. Okay. So let's define what's called a critical point. Critical point is an x value. Okay, we call this like our C, right? This is a C where something is happening. X value in the domain of our function. Okay, and it's a critical point if either f prime of c is equal to 0. So this is the value of x that makes my derivative equal to 0, or where f prime of c doesn't exist. And this part here, this second part is really important because it's going to allow me to take a look at functions that have like a cusp, right? So I've got this really sharp point that's happening. That c value, there's something really important happening there. That's a critical point. My derivative is not defined there, but it's still a critical point that I need to take a look at, okay? So either my derivative is equal to 0 or the derivative doesn't exist at that point. This is my x value, okay? The critical value is a coordinate. That's your y value. This is your f of c. Okay, not f prime of c, but your f of c. So I've got my c and then f of c. Make a coordinate, okay? Critical value can either be the y value or it can be, you can denote it as a point, actually a coordinate, okay? Critical point is just your x value. So be really careful, because if you're asked for the critical value, make sure that you give both the x and the y, okay? If you're asked for the critical point, I just need the x value. Okay. All right, so let's do some examples so you can see what we're talking about here. So example 1, this is my lecture example page for 1.5. So I'm looking at f of x equals x cubed minus 9x squared plus 24x minus 10. Now, I have to explain, we're doing these functions, we're going to find the derivative. Technically, we haven't learned the power rule yet. So technically speaking, I'm supposed to use the definition of the derivative, which is our limit process, the limit of our secant lines, right? Now, what happens in our book is we use things before we've actually learned them. So we're actually going to be using the power rule in order to get a shortcut to our derivative. Okay, so bear with me here. I'm kind of following along how our book is working it here. Okay, what we're going to talk about the power rule, you know, in the next chapter or section or so. But for now, we're just going to use it. So to find the critical points, what I'm going to do first off, I always like to plot these things out. This is my x, this is my y. You can do this on your calculator, unless you're told you're not being judged on your graphs. So go ahead and graph it. It's going to give you a visual for what you're trying to look at. So I've got some function. It's going to go like this. And when I graph this out on my calculator, it looks like that. So I know that this function is continuous. It means it's also differentiable. It's a cubic function, so I don't have to worry about any kind of discontinuities that I need to take into account when I'm doing my derivative or plotting things out. Okay, so my first step is I want to find the derivative. Remember, we're just looking for critical points. Okay, so find the derivative. So I'm going to go f prime of x equals 3x squared minus 18x plus 24. If you don't know what I did, don't worry about it. I'm going to explain this, what I just did, in the next chapter section or so. Okay, but like I said, we're using rules that we haven't technically taught you yet. Okay, so now I found the derivative. My next step is I have to set that derivative equal to 0 and solve for x. Now, you're going to go 3x squared minus 18x plus 24 equals 0. I don't care how you solve for x, okay? You want to guess and check, you want to factor, you want to do quadratic formula. You could also plot this out on your calculator, okay? My calculator will has a function where I can say, give me the 0 of that function. It's a process that I need to do on my graph, but it'll tell me what the zeros are of my function here. I don't care what you do, okay? As long as you get the right answer when you actually find out what values of x are going to cause this function to be equal to 0. So I'm going to factor this out, and I'm going to work it through. So when I factor this out, I'm going to get 3 times x minus 2 minus 4, and I'm going to solve for x. X is equal to 2 and 4. These here are my critical points. Okay, so right now I'm just looking for the critical points. Where is my derivative equal to 0? Okay, find the derivative, set it equal to 0, solve for x. Okay, this happens to be quadratic. If this was like a higher order or more complex problem, you're going to be relying on your graph to help you. Okay, if you need help figuring out how to get your calculator to work like that, come see me in office hours and we can play around with some stuff. All right, so I'm telling you ahead of time, this is a non-differentiable function. We're going to take a look at f of x equals absolute value of x. So it goes like this. Here's our function. Okay. Oh, and I shouldn't have graphed. This right here is going to be 2. These are my tangent lines here, just to show you what it looks like. Okay. Now here. Okay, so this is my absolute value function. All right. So let me think. My derivative, I'm going to have to break it up where x is positive and where x is negative. So my derivative of x is equal to -1 when x is less than 0, right? I've got this negative slope, okay, my function. My derivative of x is equal to +1 when x is greater than 0, right? This is my y equals x function, okay? And then my derivative, the function equals 0, it has no solutions. Right? We have a discontinuity here because, you know, basically what our values are, our limits on the left and the right. So our derivative at x equals 0 has no solutions, right? Okay, so with x equals 0, this has no solution. So we can't say when x is not equal to 0, this has no solutions here. So now what I can conclude is f of 0, f prime of 0, sorry, does not exist because it's not continuous. Okay, therefore, this value, x equals 0, c equals 0, is a critical point. Remember our definitions for critical point was either where, like in this part, where our derivative was equal to 0, I can solve for x, or it's where our derivative, the x values at which our derivative doesn't exist. So this is a critical point. Something interesting is happening there. Okay. Okay. All right, so I'm going to throw this theorem out here. This is Fermat's theorem on local extrema. I'm going to get into more detail about this at the end of this chapter. We probably won't get to it today. But let's say I've got some kind of a graph. Let's say my function does this. Okay. And here, where I think I've got some kind of critical value happening. And I do a secant line on both sides. So let's say I've got value here, a value here. So let's say I've got a secant line between c and c plus h. And the secant line has a positive slope, right? You can see, right? It's an upward increasing function. If I draw a secant line from, oops, I draw that very well, from c minus h to c, right? My secant line has a negative slope. Okay, my tangent line, my secant line, sorry, is downward facing, has a negative slope. Okay, so basically what Fermat's theorem on local extrema says is if f of c is a local min, in this case it's a local min, or it's a local max, then c is a critical point of f of x. It's kind of like going the opposite direction. We did the other thing where we said we're gonna talk, okay, we find this critical point and then we use it to help us figure out that it's a local min or a local max. What we're saying here is if this is a local min or a local max, then this value at which that local min or local max occurs must be a critical point. Okay, but this kind of is starting to hint at what, if you've had calc before, it kind of looks like our first derivative test. We're going to talk about that at the end of the chapter. Probably we'll get to that on Monday, okay, where I'm taking a look at what's the nature of my function, how are things changing, you know, as I approach my critical point from the left, and how are things changing as I move away from my critical point on the right-hand side. The thing to note about this, though, is that this does not mean that all critical points are local extrema. Okay, so just because some things are critical point doesn't mean it's like a min or a max. And I always think, as an example, my function f of x equals x cubed, right? So let's take a look. I'm going to plot it. My x cubed function goes like this, right? It's always increasing, okay? When I take this derivative, right, and then I set the derivative equal to 0 and I solve for x, I find here, x equals 0. It looks like it's going to be a critical point, right? Something's happening there. If x equals 0 is a critical point, right? But not a max or a min. We're going to find out later in another chapter section that it's actually what we call an inflection point, where the shape of the graph is changing, okay? So we kind of get lulled into this false sense of security. Oh yeah, look, my derivative is equal to 0. It satisfies things algebraically, but when you do other tests on it, you'll see that it's actually not a local max or a local min. It's something else, okay? But we're going to get to that later, okay? All right. I'm just throwing this stuff out for you right now, just to kind of keep that in the back of your mind. This isn't a hard and fast guarantee. Okay, so now optimization. Right, we're going to find our critical points. Critical points and our extrema on a closed interval. Starting with the closed interval, we're going to work our way up through all the different cases. The optimization, we're just going to be looking for what these extrema values are. Okay, so let me write down our theorem and then we'll go through some stuff. So our theorem says we've got these extreme values on a closed interval. Okay, so let's do this. Assume that our function is continuous and thereby differentiable, continuous on a to b, and we're going to let f of c be a minimum or a maximum value on that interval, a to b. Okay, so c is either a critical point or an endpoint. We're going to see, we're going to come at it from a different perspective. Okay, when we do this, we're looking for extrema, right? So we've got this function, we're going to find the critical points, and we're going to be given our endpoints, a to b. It's a closed interval, so a to b. I need to check my critical points, and I need to check my endpoints, and of all of those, I have to decide which one of those is going to give me a max and a min. All right, we're going to go through some examples so that you can see. And in the examples, we'll spell out our steps as we go. Okay, so example 3, we want to find the extrema of this cubic equation. 2x cubed minus 15x squared plus 24x plus, and this is a typo, it should be 7 plus 7, on the interval 0 to 6. Okay, so now I'm just going to graph this out because I like to look at it. 6, here's 0, and the function's going to go something like there. Okay. Graph, like I say, is always just for you to kind of get a feeling for what this thing looks like, and does it kind of line up with what you're finding algebraically. Okay, so the first step is, right, we know that this is a cubic function, it's continuous and differentiable. That's just my note, right? I'm looking at this interval, I can see it's continuous and differentiable. Okay, so my first step is I need to find the derivative, set it equal to 0, and solve for my critical points. Okay, so I'm going to say f prime of x equals 0. So I'm going to do this. I'm using my power rule. Remember, we're pretending that we know the power rule. We're going to pretend that we're using the definition of the derivative because officially we haven't had the power rule yet, but we're doing it anyway. 6x squared minus 30x plus 24. Okay, I'm going to factor this out. So 6x minus 1, x minus 4. Like I said, I don't care how you solve for it. You can plug this into your calculator and get the x values. Maybe you just want to tell me by my calculator. I got this. X equals 1 and 4. These are our critical points. Okay. Now what I need to do is I have to check my function values, not my derivative, but my function values against the critical points and the endpoints and see which one gives me the biggest, that'll be my maximum, and the smallest, that'll be my minimum. Okay, so we're going to compare values. I'm going to make a table. So I've got my x value. And I'm going to just note to myself, is this a critical point or an endpoint? So I've got x equals 1. This is the critical point. I've got x equals 4. This is a critical point. I've got my interval, my endpoint. So I've got my 0. This is my endpoint. And I've got 6. Okay, that's an endpoint. Okay. Now I have to plug these into my function. No, it's not the derivative, right? I mean, like, if you did the derivative, you're going to get zeros on 1 and 4, so that's not going to help you. That helped you to figure out what the critical point was, but now I'm plugging it into my function. I want to find out what's the value there. So I say f of 1 equals, I plug it into 2 times 1 cubed minus 15 times 1 squared plus 24 times 1 plus 7, right? I'm going to get some value. So f of 1 equals 18. F of 4 equals a minus 9. F of 0 equals 7. F of 6, I'm sorry, I gave it away. F of 6 equals 43. There. Okay, now when I look at this, right, I'm identifying what values are my biggest and smallest. That's small, that's big, right? So this is a minimum. This is a maximum. Okay, so what we do is we write it like this. What are our x values? X equals 4 gives us a minimum. X equals 6 gives us a maximum. Okay. I needed to check my endpoints because it's a closed interval. My function is going to be defined here, right? So this was, that's 1, this is 4, okay? This right here is my minimum. This right here is my maximum, okay, along this closed interval. I must check my critical point and my endpoints, okay? Okay, so let's try another example. We're going to do a function with a cusp, so it's not quite as obvious. So I've got this function here, 1 minus x minus 1 raised to the 2/3 power. And I'm looking on the interval minus 1 to 2. So I like to plot these things out. Minus 1, 1, 2. Okay, so these are my bounds, my endpoint values. So this is my function here, goes like this, down like that. You can plot on your calculator and take a look too. Okay, so the first thing is we have to find our critical points. Okay, so I have to take the derivative. Remember, if this doesn't make sense because we haven't had the power rule yet, don't sweat it. We're going to learn that soon. Okay, so right now I'm going to go minus 2/3 x minus 1 to the minus 1/3, which I'm going to write this out as a fraction so I can see it a little more clearly. So minus 2 all over 3 x minus 1 to the 1/3. So you can see here, right, if I set this equal to 0, there's like no value on here, right, that's going to be able to cause the derivative to equal to 0. If I plug in x equals 1, right, x equals 1 in theory, like that could possibly, it's going to give me a divide by 0 error, but that's like the only place where I'm going to get a value where my function is going to be equal to 0. Okay, so I'm going to write this down. So f prime of x equals 0 has no solutions because f prime of x is not equal to 0. Right? I can't plug in. I'm going to get a domain restriction if I plug in x equals 1. So this is because f prime of x does not exist at x is equal to 1. right? So this becomes our critical value. This is the spot where our derivative doesn't exist. That was the other definition of our critical value, critical point, sorry. So x equals 1 is critical point, okay? So we found our critical point. We have our boundary values. Now we have to compare. We're going to set up a table. Okay, so I'm going to set up x values. Remember, I'm going to check my critical points, and my endpoints. I'll specify which one it is. So 1, x equals 1, critical point. Remember, I'm plugging this into my function, okay, not my derivative, my function. I also check my boundary, my endpoints, endpoint, and 2. This is my other endpoint. And I'm plugging those into my function. Right, notice I'm not plugging into the derivative, but the function. So I say f of 1 equals 1, right? So I go back up here to this, right? And I plug in x equals 1. I get 0 raised to the 2/3 power. 1 minus 0 is equal to 1. F of minus 1 is approximately equal to, I'm going to round, minus 0.95. F of 2 is equal to 0. And so on here, I take a look at what are my maximum and my minimum values. This one here gives me a max. This one here gives me a min. Okay. So I'm going to summarize that. Say x equals 1 is a maximum. X is equal to minus 1 is a minimum. Okay. On my interval for this function. Right. This one. X squared minus 8 times the natural log of x along this interval of 1 to 4. So I'm going to graph it out. So it goes something like our interval here, this. I'm sketching it, right? I'm not trying to do this, like I'm not an artist here, but I'm trying to just get a rough sketch of what's going on so I can visualize what things look like. Okay, so my first part is I have to find the critical points. Okay. So I'm going to take my derivative. F of x is equal to 2x minus 8 over x. If you don't know how to do this, don't sweat it. We're going to get to it. I'm going to set that equal to 0, and I'm going to solve for x. Okay, so you're going to bring it over to the other side. You're going to cross multiply, and you're going to find that x is equal to positive or negative 2. Okay, after you're working your way through it. So x is equal to positive or negative 2, but only positive 2 is in our interval. Okay, so I'm going to ignore negative 2. Okay, even though that's a root of this, but I'm not going to worry about it. Right, for what I'm trying to do because my interval. Okay, now I'm going to compare values. Okay, so let's set up our table. So our x value, remember we have to do critical points and our endpoints. So I'm going to use positive 2. This is the critical point. I'm going to do 1. This is our endpoint. I'm going to do 4. This is our other endpoint. I'm going to take a look at my f of x at that particular x value and see what we get. So wherever I see an x on my function, so I'm going to get 2 squared minus 8 times the natural log of 2. I'm going to get a value. And I'm going to plug that in. So f of 2 equals approximately minus 1.55. Don't rely on the graph. Make sure you're actually showing the table. Do f of 1. I'm going to get it's equal to 1. And then f of 4 is equal to approximately 4.9. Okay, so from my table, I'm going to look to see which one's big and which one's small. smallest value along the table, biggest value along the table. So let's summarize. X is equal to, so let's write this down. This is, so X equals 2 gives us a minimum. X equals 4 gives us a maximum. Okay. You must make sure you plug it into f of x. Set up your table. You're checking critical point and endpoints. Okay, in your function, not your derivative. If I plug this into my derivative, I'm going to get 0. It's not going to help me. So make sure you plug it into your function. And don't forget your endpoints. Okay. So far, so good? Okay. All right. So there's I'm going to throw this out here. It's called Raleigh's theorem. It's a special case. It sort of forms the basis for the mean value theorem. So what I'm going to do is I'll draw a picture at this interval a and b. So my function kind of does some stuff. Right, here's a, here's b. Here's b. Okay, now here's our tangent line. Okay, I just drew a picture. Let me write the words so that the picture will make sense. Okay, so here's our function. All right, so we're going to assume that f of x is continuous along our interval a to b, which means it's also differentiable along our interval. Okay. If f of a equals f of b, right? So here, that's the same value. So this is f of a equals f of b equals this value right here. Okay, the function is the same value right at that spot. There's a symmetry there. F of a equals f of b, and b isn't equal to a. Then we can say there exists a number c right here, which is between a and b, such that f prime of c equals 0. So let's summarize that. My function, right? I've got my function f of x. I've got this interval a to b, right? Okay, so a and b are both have the same value, okay? So if I were to make a secant line between these, the slope of the secant line would be equal to 0, right? That's my secant line between these 2 points, right? If this is true, okay, here, and a isn't equal to b, then I have some kind of a value c where I can find a tangent line that's going to be horizontal. So the slope of the tangent line equals the slope of the secant line, and the slopes are equal to 0. Okay. That's Raleigh's theorem. We're going to use that. It's like a special case of our mean value theorem. We're going to get to that in just a minute. So let's do an example on Raleigh's theorem. Okay, example 6. Okay, x to the 4th minus x squared. Okay, so we want to be able to verify this. So x to the 4th function, right? It's positive. It's kind of got this W shape that it's making, x to the 4th minus x squared. Okay, so f of x is continuous and differentiable on our interval. Okay. F of 2 equals f of minus 2. Okay, let's just prove it to ourselves. So f of 2 equals 2 to the 4th minus 2 squared. And f of minus 2 equals minus 2 to the 4th minus a minus 2 squared, right? So it's an even power on each side. You can see how it's going to be equal. Okay. So f prime of c equals 0. That's Raleigh's theorem, right? That means somewhere there's a c value between minus 2 and 2 that's going to have a horizontal slope on its tangent. So let's check it out. So f prime of x equals 4x cubed minus 2x. Set that equal to 0, and I solve for x. So I can factor out a 2x. I'm going to get 2x squared minus 1 equals 0. That means I'm going to get c, this is my c equals x equals 0, and plus or minus 1 over radical 2. Okay, so all of these values here, 0, plus or minus 1 over radical 2, they are all within our interval. This is where our tangent line is horizontal, which means our slope is equal to 0. All these values where the tangent line is horizontal are within our interval, minus 2 to 2. And that was Raleigh's theorem. Raleigh's theorem just said if you had this interval here where the function is equal to itself, right? The function at minus 2 is equal to the function at 2. That means I must have some, value of x within here where my slope of my tangent line is going to be equal to 0. Tangent line is going to be horizontal. In this case, we actually have 3 values, which makes sense because this is a W-shaped function, so I'm going to have multiple stuff going on. Okay, so let's use Raleigh's theorem to help us talk about the mean value theorem. It's a pretty important theorem. All right, so let me draw a picture and then we'll put all the words to it. So here's my axis. And let's say I've got some function. It's doing something like this. Here's my function. Okay, so I have an interval. So here's my A. I'll try to make it exaggerated so that you can see. So I've got this, here's my secant line. So I've got a secant line going between A and B. Okay, along my function, secant line. Now, the mean value theorem says, right, that within this, I can actually find that there is a tangent line These two, the tangent line and the secant line, have the same slope. They're parallel to each other. Okay. Okay, and what that means is, let's draw this out. So my tangent line cuts down, there's a value of C, right? So if I have some kind of secant line between A and B, right, there's some kind of a tangent line that will have the same slope as my secant line, and I can use that to help me solve for C, okay? At what value of X is that tangent line going to be equal to my secant line? So let me write it out in math speak, and then we'll do an example. Okay, but this is where we're coming at, okay? So let's say we've got a secant line between 2 points, which is A, f of A, and B, f of B, right? So A and B form our X points, right? X values, and then f of A and f of B form the Y coordinate for that. And this is on our graph. And this secant line is parallel to at least one tangent line. It could be multiple tangent lines that it's going to be parallel to, but let's say it's parallel to at least one tangent line in the interval A to B, such that C is between A and B. Okay. So let's write this out. So what that means is I've got my tangent line at C, my slope, is equal to f of B minus f of A all over B minus A. So let's write down what these pieces are. This right here is our slope of the tangent line. Okay. And this is our definition. This is our slope of the secant line. Okay. So Raleigh's theorem is just a special case where the slopes are equal to 0. Okay, and I can find out what that is. But here, not necessarily is it equal to 0. Okay, but we're going to use the mean value theorem to find this value of C that's parallel to our secant line. That leads us to example 7. Okay, you guys all have that? All right, so I'm just going to graph this out here just so we can see this. It's a A equals 1, B equals 9. Okay, so it's going to go 1, 3, 5, 5, 4, 2. I'm trying to come up with a graph here. Here's my f of x. Okay. So now we're looking at A equals 1, B equals 9. So I'm going to make a secant line from here to here. So I need to find out what that secant line slope is. Okay. So the first thing I need to do is, what is the slope of the secant line? Okay, between A equals 1 and B equals 9. That's step 1. Okay. So I'll say f of B minus f of A all over B minus A. Our secant line, just regular slope, rise over the run. Okay, so f of B, so this is going to be radical 9 minus radical 1 all over 9 minus 1. Radical 9, 3 minus 1. This is going to be 9 minus 1 is 8. So this is, we're looking at 2/8. This is 1/4. That's the slope of our secant line, right? It's positive. This is a positive slope here. Okay, good. All right. So now our goal is, right, I need to find a value of C that's going to give me the same slope, right? Or in other words, I can say, if I make my tangent line have the slope equal to 1/4, at what x value does that occur, right? Okay, so we'll say tangent line with slope equals to 1/4, and I got that from here, occurs at which x value? We'll say x equals C equals what? What is that C value? So that's what we're trying to do here. Okay, so watch what I'm going to do. I'm going to say f prime of x is equal to, I find my derivative. So my f prime is x to the 1/2. My f function is x to the 1/2. My f prime is 1/2 x to the minus 1/2. I'm going to set that equal to 1/4. Be really careful. We're accustomed to finding the derivative, setting it equal to 0, solving for those critical points. In this case, we have what the slope is going to be for our tangent line. We want to find out what x value is going to give us the slope of 1/4. Okay, so now I'm going to rewrite this. So I'm going to change this around. So it's going to look like 1/2 times 1 over radical C. So I'm going to plug in C for x. Okay, C for x. This is my f prime of C. Right, and I'm going to make that equal to 1/4. So I've got to like cross multiply because I want to solve for C. What C value is going to give me that? Okay, so I'm going to cross multiply. So this is going to be, let's see, it's going to be 2 radical C equals 4. I'm going to divide by 2, sorry. And I'm going to say radical C equals 2. And remember, I want to get C equals, I have to square both sides, so C equals 4. Okay, so let's just draw that on my graph. So C equals 4 here. I have a tangent line with slope equals 1/4. And this is secant line, slope equals 1/4. So these two, it's hard to see on this graph, but those two, the green and the red lines, are parallel to each other. So my C equals 4. So what this means is that f prime of C equals 1/4 happens when C equals 4. Okay, this C equals 4 lies within our interval 1 to 9 and satisfies f prime of 4 equals 1/4. That's f prime of 4. Okay. So we used our secant line. We found the slope on this for the secant line. We said, what's the value of C where the tangent line is going to have the same slope, right? They're parallel. That means they have the same slope. Okay. Our mean value theorem. I think I'm going to wait till Monday to start talking about the rest of it. Rest of 1.5 has some really interesting stuff. How do we check to see, min, max, our first derivative test, all those things. I want to wait. I don't want to be rushed for it. We only have like 5 minutes left anyway. With that said, does anybody have any questions? We have homework due today and we have a quiz this afternoon. Well, starting today, could go till tomorrow, depending on when you start it. You guys don't have any questions, then I'll just end early. Let me see.
Sorry, I had a question. For like finding the derivative using the definition, are we allowed to just use the rules that we learned yesterday? Like if there's 4x, can we just say that the derivative of that is 4 within like a bigger equation, so we don't have to? Like, yeah.
I hear what you're saying. I gotta tell you, so it's the book is kind of funny where we're constantly using things that we haven't officially learned yet, right? Like we used the limit before we actually learned what the limit was. Now we're doing the power rule before we've actually learned what the power rule is. For the quiz today, you'll want to make sure that you use the definition of the derivative, which is your limit process, right? I think if you're doing questions like in 1.4, if it tells you to use the definition of the derivative, then you should. If it's like a much bigger equation, right, then you can use those little special rules, like the derivative of a constant. I think we gave like x squared and x to the 1. You can use those because that'll help you simplify it. But especially if it says use the definition of the derivative, then just do the long way. I know it's frustrating, but but then when we get to 1.5, yeah, we get to 1.5 question homework questions, then you can start kind of doing the shortcuts, okay? Because 1.5 we're doing the shortcuts because we're learning more complex stuff. I kind of don't know why they don't just introduce the power rule before we get into critical points and stuff, but I'm just doing what, the syllabus comes from the department and the book comes from the department, so I'm kind of working with what I've got here. So yes, for the quiz, if it says definition of the derivative, do the long way. Okay.
Yeah, okay, thank you.
I see a question on the chat, says question 57, is that 1.4 or 1.3? It must be 1.4. Okay, give me a sec. 557. Okay. All right. Let me move this out. All right. Oh yeah, 57 is pretty long. Okay, so let's go through. I'll try to go through here. So this is chapter 1.4, and this is question 57. Okay. So we have an x-axis travel, and we're given the velocity v of t equals 2t squared minus 42t plus 180. And I think that's meters per minute is what I have for units. Okay. So we're looking for the speed function, the rate of change of the speed, and the 2 points for the speed is not differentiable. Let's see, I have to keep my eye on the time. I'm not supposed to keep you guys past time. All right, so our speed function. So what we want to do is we want to find regions in which v of t is positive and negative, because speed is speed's always going to be positive, right? Like velocity is a vector, but I have to be able to find where it's positive and negative. If it's negative, I have to make it positive so I can just add everything up. Okay, so I'm going to go 0 equals 2t squared minus 42t plus 180. So it's a parabola, right? I've got this. I have to find these regions here where it's negative and then make it positive so I can just then add up all that stuff. So I start checking around. So let's see, I'm sorry. This is equal to t minus 15. I'm going a little bit fast because I don't want to run out of time. T minus 15 and t minus 6. So that gives me some boundaries. So this is 6 and 15. So I have to check to see, is it positive or negative? So I'm going to say a V of 0. I'm going to plug it in. I get 180, so that's a positive number. V of 10, right, that's in between this interval here, I'm going to get minus 40, which is a negative number. And then V of, sorry, that's a V. V of 20, which is in this interval here, I get 140, which is positive. So, and I'm basically before 6, I'm looking at positive values. Between 6 and 15, I'm looking at negative values. And greater than 15, I'm looking at positive values. So anything between 6 and 15, I have to make positive. Right, so then my speed, as a function of time, looks like 2t squared minus 42t plus 180. When I say t is less than 6 or t is greater than 15, and I say it's minus 2t squared plus 42t minus 180, right? So I negated all of these terms, and that's when t is between 6 and 15. So that's my speed function, right? Speed needs to be positive. I have to find out where it's negative and then make it positive. So if it's negative, this is how we take the absolute value of something. I make it positive. Okay, that's part A. Part B says, what's the rate of change of speed? So speed of t equals v of t when v of t is positive. So minus infinity to 6, right? My speed is equal to the velocity. Okay, so then my rate of change is going to equal to 4t minus 42. Okay, within that interval here. Okay, that's where it's positive. And then I forget what else. Why do I have minus 38? I must be checking something else. So then see, I just have my solutions here. I'm trying to figure out. So C says 2 points where the speed is not differentiable. So I say t equals 6 and t equals 15. Okay, because I have transition points here. So my S prime of t equals 4t minus 42 if t is less than 6 and t is greater than 15. And then my rate of change is equal to minus 4t plus 42 if 6 is between t and 15. So it's like, remember how we had to specify, we had to make it negative, which means that my derivative is going to be different. So my rate of change is not going to be definable. You guys, I think, and I can use the limits to help me define that too. We're running out of time here. I don't want to keep you for other classes. I noticed somebody has a question on 26. If you want to make it to office hours today, I'll answer it in office hours. If not, email me the question if you can't make it to office hours, and then I'll do the solution and post it, okay? All right, because I don't want to keep you, I'm actually not supposed to keep you guys past the class time, okay? All right, you guys, good luck, and I'll see you next week. Bye-bye.
Thank
you.
you.
Thank you.
Thank you.
Thank you.
Bye.